Okay, so I think people should be able to see my screen now. Is that visible?
Yes.
All right. So I'm going to give a quick primer today on how to get JIT verbose logs and how to read them. But I need to go through a couple of things first. So what is the verbose JIT log? It's basically a summary of what methods were compiled by the JIT and some of the compilation heuristic decisions that get made while the JIT is operating inside the JVM. It is not the more detailed logging that's available for how the compiler optimized and generated the code for a method and a tree of methods that get inline. I can do that another day, but that's not something that I'm going to be talking about today. That's not what the verbose log is for. So before I can actually talk about the verbose log format, there's a bunch of, you need to understand a little bit about how the JIT itself is actually working so that you'll recognize the things that are in the log entry. So this is a quick primer. I'm not going to go through this in detail, but primarily I wanted to just point out that methods obviously start out interpreted like they do in just about every JVM. And then there are a sequence of compile levels, we call them optimization levels, that are sort of temperature-based, cold through warm, hot, and scorching, which basically trade off how much compile time we're willing to spend for how much faster the code we get out of it is expected to be. And so in a verbose log, you're going to see entries that list things like the optimization level, cold, hot, warm, etc., that was used to compile a particular method. There are a variety of different heuristics used to decide which ones. I'm not going to go through that here, but there's a little bit of information in the slide. And then there's a few interesting names that you'll see in verbose logs, which I won't talk about here, but it could serve as a reference for you if you're playing around with your own verbose logs. Okay, I am now going to try to share a command line prompt. See how this goes. Can everyone see that? Okay, great. So I work on a MacBook, which doesn't unfortunately run OpenJ9 natively yet. My fingers keep crossing for getting it soon, but I can run it using the Docker images that it. So we can verify that this is OpenJ9 that's being used as the JVM inside this package, and we're running with OpenJDK 1.8. So I'm actually going to use the very simplest Java application you possibly can, which is not hello world, but is actually dash version. So if you want to generate a verbose log with OpenJ9, all you have to do is add this -xjit verbose option, and that will helpfully provide a whole bunch of information about what the JIT's doing. Now that's a lot of stuff. So let's scroll back up here and look through what's actually here. So there's a bunch of hash info stuff that gets printed out first. These are things that are relevant if you're trying to understand what JIT you're using. So for instance, you can get the SHAs of the JIT and the date of the JVM. You can get some information about the processor that's running that the JIT sees and how many processors it thinks it has access to. There are sections here for the AOT options and JIT options. I'm going to ignore the AOT options for now. But the JIT options, you can see under the options specified, it actually includes the verbose. That's the setting that I added to -xjit. So if I added other options, it will show here. And then a few other sort of interesting things that are relevant for the JIT's operation. Start time, memory, how much of the CPU we think we have we're entitled to use, and so on. And then a sequence of lines to describe the methods that are being compiled. So this first line here starts with a plus. The plus means that this is a successfully compiled method. If it started with an exclamation mark, it would be a failed compilation. There are a few other characters that can be used. And each line basically corresponds to a single compilation event, right? So in this particular case, at the cold optimization level, we compiled getCaller class. We generated the code at this code range. And there's some details about the compilation queue statistics when we did the compilation. There's some internal pointer stuff. This method is actually just a native method. So what we're actually compiling here is an accelerated JNI transition into this native getCaller class function. That's why the bytecode size is so small. It's just a call. And then some other stuff. And so you can see there are a bunch of different lines for different things as we're compiling things. And eventually you can see the actual output from the dash version output. That's this stuff here mixed in. I'll talk about that in a sec. And then once we're done, there's still some stuff being compiled on shutdown. So that's a little bit interesting. Now, you might not kind of like all of that stuff to be embedded in your output. So there's actually an option, vlog, which you can use to store it to a file. So now we just see the output normally. And if we look in the current directory, there's a file called vlog file. And it's usefully suffixed with some interesting stuff here, just so that you can distinguish if you have multiple JVMs running, or if you do multiple runs, you don't necessarily just overwrite the verbose log file from any one run. So it's tagged with the date. This is the time, and this should be the process ID of the JVM that ran. If you don't like having that suffix or all that suffix logs there because it's hard to find things, or you actually do want it to be override, you can do that. And now if we look inside our command, we have vlog file, which is the same thing that we saw with all the wonderful output that we had before. Now, none of those compiles are very interesting because by default, we don't actually do a whole lot of compilation during dash version because it's very fast. There's not much time to do very much compilation. So I'm going to fake it out a little bit and add an override to the JIT heuristics to say, I want you to compile after 5 invocations. And so that's going to generate a whole whack load of more stuff. You can see now we have some warm compiles in here. And they're methods with, more interesting methods. They have a bytecode size of 72. And the queue is actually getting, much larger as we get through the compilation here. And you can see even at the end, if we go to the last successful compile here, there were still 324 methods queued to be compiled when we reached the end of the JVM. The JVM shut down and just gave up on compiling that. That's because I asked it to compile so many things. And you can also see some examples of some failed compiles. These ones are failing because the JVM is in the process of shutting down. So you can't shut down and generate code at the same time. So we fail the compiles and then we get out. There are some reasons why you might fail compiles during a run for less catastrophic reasons, but I don't really have time to talk about that too much here. The sort of last topic that I wanted to bring up is that there are even some sub-options that you can provide on as part of verbose that will give you some additional information. One of the most important or useful ones is this one. We use this one all the time. It adds some information into the verbose log that makes it a little bit better. You can understand a little bit more about the performance of what's going on with the compiler threads. So for example, well, let's just pick up this guy. So it adds this new section to each verbose entry. So you can get the time that it takes to do the compilation. So that's 660 microseconds it took to compile hash table entry.getValue at warm. And it allocated this amount of memory while it was doing that. So, some methods will use more than others. If we actually had something being compiled that's scorching or hot, it would be generating a lot more memory or using a lot more memory to do the compilation. Finally, the last one that I'll show you, which is one that I like to advertise a little bit, even though it's not perfect. So you can put different sub options together. So compile start is an interesting one. Oh, I didn't even mention compile start before. Sorry. Compile performance uses compile start as well. So it basically prints out a line when you're about to start compiling something. So that's this compiling. This means I'm about to start compiling hashtable.get. And then there's a follow-on line that would be the plus or the minus in this particular case, I guess. Here's the corresponding, sorry, I failed to compile hashtable.get. That's an event called compile end. So I'm going to ask for both compile start and compile end. So I know the boundaries of a particular compilation. And then there's an interesting sub-option called inlining that people always ask questions about. And because we use the vertical bar, we have to protect that from the shell. And then the other thing that doesn't work very well in this one, which we should really fix, is that it's not really good for multiple compilation threads, which are on by default. So I'm going to set compilation threads 1 and look at compile start, end, and inlining, and hopefully this will lead us to an interesting compile somewhere in here. It worked before. There we go. Here's a good one. Put val. So I'm going to just highlight the whole compilation event for put val here, which is all of this. Hopefully you can see all that. So this is the compile start line saying that we're about to start compiling hashmap.putval. This is the final, we compiled it at warm and all of its details, and it took, you know, we don't have the time in this one, so it doesn't show the time. But the inlining information tells you what inlining was actually performed as part of this, and it didn't actually inline anything this one. Sorry. This shows lots of stuff that it could have inlined but didn't. Let me see if I can find one that did inline. One method, that's not very interesting. Two methods. Of course, this worked in the demo that I did myself beforehand. Let's see if we can get a different run and have some. There we go. That's better. All right. This one's even shorter to do. Okay, so now we're doing string.equals. In this case, we actually inline 7 methods into the top level string.equals. It first lists the methods that actually did get inlined. So that's this list here, and it numbers each one of them so that it can refer to them and describe to you the tree of how things got inlined. So -1 in this particular case is the top level method that's being compiled. So we inlined 3 methods into the top level compile, and then we inlined another 4 methods into this number 2 guy, which is the, if you go across, it's this guy, and that's string.regionmatches internal. And so each line gives some data about the method that's being inlined. There's a pointer here which corresponds to, it's an internal pointer called a J9 method, which you can link up to the names. It's hard to see, but there's actually an @22 or an @number at the end of all of these. That's a bytecode index that describes the call that's being inlined. And then this stuff on the right shows the details of the method that actually got inlined there, right? So string.length internal got inlined at a call at bytecode index 22. It also got inlined at a call at bytecode index 28. And then region matches internal got inlined at a bytecode index of, or a call that's at bytecode index 104. And so you can kind of reconstruct the tree of inlines that's happening and what's being inlined and what isn't being inlined into the method. And that's basically where I was going to stop because I think I've run out of time and the freezing probably didn't help. There's lots more to learn here, so I guess I'll just sign off by saying, you know, if you have any questions or if I wasn't clear about anything, feel free to ask questions on our Slack channels, or you can send me email or talk, you know, direct message me on Twitter, whatever. The preferred way is probably to talk on the Slack channel, just because there's a bunch of people that can help with questions, and we can all see the answers to what's being asked. And I'll stop there and pass back.
Thanks, Mark. Is there any questions from anybody on the call today?
So I did have just one question out of interest while you've done all that, Mark. So the example that you did, which I think was string.equals,
yes.
Am I right in thinking that now every invocation of string.equals will invoke exactly the same code with all those same methods inlined as that compilation that happened then, and that will be true until the JIT recompiles string.equals?
It is possible for inline code bodies to be invalidated inside a compiled method. So it's not necessarily the case that you'll continue to execute those inline methods as part of the compiled body for string.equals. But that's obviously the way we prefer it to work, right? So if there are invalidated assumptions, maybe that would cause it. But as long as everything goes smoothly, if you call string.equals, you will end up calling all of those inline methods as part of string.equals, as opposed to doing separate calls to those methods. Does that answer your question?
Yes, thank you. Yep.